Today we're going to extend the parser with two new things. So one, my friend Demetrius pointed out that we didn't have a way to continue parsing at the current precedence level. So if we had something like 2 times 3 plus 4 times 5 plus 6 times 7, we would only parse this weak arithmetic expression that bound together these two, but then we wouldn't go on to parse this one that did plus 6 times 7. So really, in order to do this, we're just going to take this as the left-hand side, right? This was binding the most tightly on the left-hand side because we're doing a left-hand side derivation parsing. And then we're going to use that as the left-hand side for the subsequent expression that has this 6 times 7 in it. So this is what it'll look like. There'll be a node for the add that has these moles inside, and then there will be a node for the following add that uses this as the left-hand side and this is the right-hand side. And then following that, we'll do let bindings. We'll introduce the idea of a name that can refer to an expression into the grammar as well. Okay, let's start by making our test case. Test parse multiple weak expressions. So these are all going to be lined up in a row. The program is going to be 2 times 3 plus 4 times 5 plus 6 times 7. And so we're going to get an expression out of that. And we're going to check that we have an add. And that's going to have two adds. Or let's see, the add node is going actually to have a add on the left-hand side and a mul on the right-hand side like we drew on the board. Okay, so this one doesn't reach the end of file because we don't parse multiple expressions at the same level. And so what we're going to do now is we're going to go into our parse weak arithmetic. And what we're really going to do is we're just going to say, as long as we can see a plus, we're going to keep parsing out this left-hand side. So we're going to say, while true, we're going to look ahead at the token and see if it's a plus. And if it is a plus or a minus, then what we're actually going to do is we're going to say the term becomes, the left-hand side becomes the result here. So term equals, and then we can continue this loop. And if we don't see any of those, we break out and we say, all right, now we actually don't see any continuation character at this current precedence level. All right, and so here we've made a syntax error. We need equality. Okay, so basically what this lets us do to walk back through it is we look for a term, and that's our left-hand side. And then we look for our continuation character at the current precedence level. So that's something like a plus or a minus sign. And if we see that, then we go and we parse our current term like normal. But instead of just returning it, we actually stay at this current precedence level and see if there's another plus past the result of that expression. So really we have to do this for each of our potentially returning, for any of our operators that can string along at the same precedence level. So here we're doing our look ahead. We did it a slightly different style than we did in the other one, but term equals div, and then we continue, term equals mul, and then we continue. But here, if we didn't see any of them, we break out. So we need a test for this where we do 2 times 3 times 4, multiple strong arithmetic expressions. And so this one will have a mul, and on the left-hand side we will have another mul, and on the right-hand side we'll have a number. Okay, strong expressions. Okay, and so here we have to check that these actually contain what we think that they do. So we'll say add is AST children 0. And so this is the add here. That's the 2 times 3 plus 4 times 5. So this one's going to be, let's say, left-hand side, outer left-hand side is children 0. Outer right-hand side is children 1. And let's check that that one has 6 times 7. Outer right-hand side is a mul. And outer right-hand side, children 0 should be the number 6. And the outer right-hand side 1, number 7. Excellent. And so now if we check our left-hand side should have 2 strong arithmetic multiplies inside. So then we should be able to assert that outer left-hand side, children 0, is an instance mul, and that the right-hand side is also an instance of mul, and that this one is number, the left-hand child is number 2. Okay, so there's some more assertions that we really should make here. And really we should make a generic matcher so that we don't have to type all this stuff out every time. But also keeping test cases simple has its own virtues. But this looks like it's basically doing what we expect it to do. So here we could check that the number is actually the number 4. So it's pretty a simple concept, just stringing along at the current precedence level. So we create our left-hand side expression because that one bound the most tightly by virtue of showing up on the left-hand side. And then if we see another character at the same precedence level, we make that left-hand side expression into a sub-expression, a term, and then we continue on from there. So if we go back to our grammar, it's really that if we see term times term, that we will accept any number of times terms here. And then we can actually remove this one because it's redundant. Term slash term, and any number of those. Well, technically, we actually have to take the union of those two productions, but this is roughly the idea. Okay, cool. So now we're going to introduce a new idea, which is let bindings. So for let bindings, we actually have to create something where we can parse identifiers, and we can look up whether identifiers are present. So we'll have something like an expression is a weak arithmetic expression, or we'll have a let keyword, and then we'll have, let's say, some name, and then the equal sign, and then we'll have some expression, and then we'll have the in keyword, and then we'll have some other expression. So this is a pretty interestingly different one from the ones that we're used to, but it's very easily signified up front by this let keyword. So we can say if self.peakt is keyword, keyword.let, and here I'm just kind of speculating that we're going to create some functions. This is less of the TDD way, more of the speculating what we're going to build way. So we're going to say if the keyword is let, then we're going to do self.parse let expression. And if we don't see the let, then we'll try to parse it as a weak arithmetic expression. So we don't know what peakt is keyword is. So let's go look at our peakt. Okay, so we have our pop t or error. So we're going to say peakt is keyword, self target will be the keyword, and we're going to return a boolean to say whether the peak is a keyword. So here we're going to say if we're at the end of file, then we do not see a keyword. If we are not at the end of file, then we're going to say that the look ahead token, we're going to return that the look ahead token kind is the keyword kind, and the token value is a keyword with the given target. Okay, so keyword is not defined. We have to define our enum of keywords. So remember, a token holds some value that was previously just a string. Now we're going to say it's either a string or a keyword. So I guess we could do that, or we could actually just put the keyword as a string in that value payload. maybe we'll actually just put the value as a string. So keyword is going to be a special token kind. So target will be a string, and keyword is not defined. Okay, so if peak t is keyword, let. So now we're switching from using explicit enums to using just stringy values for what the payload was. Okay, it doesn't like our use of at end of file. So let's see how we defined end of file here. Let's see. All right, let's leave out the end of file condition for now, also because we're inside parse expression, and so if we're at the end of the file, this will raise an error currently anyway. Okay, so let's see. Parse let expr. We don't know what that is, so we have to define what that is. Def parse let expr self. It's going to return an expression. It's actually going to be a let expression, so we will actually subclass it as let, and for now we're going to raise a not implemented error. Okay, let is not defined, so we have to define a let expression. And a let expression has the left-hand side, which is the name, and it has a right-hand side, which is the expression that binds to the name. And then it has the body, which is an expression that can use the name now that it's bound. So we're going to do expr super init children are left-hand side, right-hand side, body. Okay, and we don't know what a name is. So on the left-hand side, a name is actually not an expression per se. So we're going to have the idea of a name definition AST node. But a name definition AST node, it's basically just a string. So maybe what we're going to do here is we're going to say that there's a stringy attribute, which is not an AST node, not an expression, that we call the left-hand side, which is the name that's being bound to. So here we find that the parser is happy, but that's because we didn't define any tests, so it's just not blowing up. So test parse let binding, or let expression. So our program here is going to say like let x equals 2 in x plus x. And that's an expression. So this is going to be the left-hand side, this is going to be the right-hand side, a number, and this body is a weak arithmetic expression. And so we're going to say parse program. We're going to assert that the AST node is a let. We're going to assert that the right-hand side, that the left-hand side is x. We're going to assert that the right-hand side is the number 2, and we're going to assert that the body is a add node, and then we're going to assert that the body's child 0 is the name x. So this is actually a name reference. Let's call it a name ref, and that the right-hand side is also the name ref x. Okay, so now our scanner is blowing up because it's seeing something that it doesn't understand. So raise not implemented error. It would be more helpful if this would tell us what the character was. So it's seeing the letter L, and it doesn't know what the letter L is. So if we get to the end of this, and it's not any of our special characters, we have one of these kind of c.isDigit cases where, oh yeah, it's some kind of number. So here, if it's a letter character, so let's say we only accept lowercase characters for now. So if C is between A and Z, also we're saying in, I guess, the Roman alphabet, then we are going to return self.scan identifier or keyword. And so this is important because, and we're going to give it the start position. So this is important because identifiers, so if I say let then let is actually a keyword in that case. That's what the token kind is going to be. But if I say let foo, then that's not the keyword let anymore. So I actually have to look at the characters and say, oh, do those characters mean that this thing is a keyword? And otherwise I return it as an identifier token. So here we're going to make a helper that was called scan identifier keyword. And we got the starting character, I believe, and the start position. And we're going to give back a token. Okay, so here we're going to say while the peeked at character, so we need to look at what the character is, peek at a character, if the character continues an identifier. So we're only going to have identifiers include those lowercase characters. So we'll say is identifier rest, because maybe we'll actually include numbers as well in the rest of the identifier. So an identifier can't start with a number, but a number could be in the rest of the identifier. Then what we're going to do is we're just going to accumulate up what the characters are that make up this identifier. So it starts off with the one that, let's call the start car. All right, so we start off with that start character. If this is also a valid identifier, then we're going to pop it off the character stream, and then we're going to append this character to it, and then we're going to keep going. Otherwise, we're done. We peeked at the character, it wasn't an identifier continuing character, and so now we have all the characters before something terminated the identifier. We can't continue the identifier any further. And so the identifier, which also may be a keyword, so let's call it identifier keyword, is the result of joining together all of these characters. And right now we only have one keyword, so we can say if identifier or keyword is let, then we're going to return a token that's token kind keyword. The payload is identifier or keyword, and then we have to give it a start position as well. And if otherwise it's not let, then we say it's token kind dot identifier or keyword start position. So this is the value payload in both cases. So we had this little inline test here for whether a character started an identifier. So let's make this a little more formal and say is identifier start C, and then we'll create some helper functions that say whether a character starts or continues an identifier. Is identifier start. We're going to return, we'll do the same thing we did before, and we're going to have is identifier rest. And for this one, we're going to say either it's the start of an identifier character, or we'll also accept digits here in the remaining character. So it can't start with a digit, but it can continue with a digit. So sorry, I meant to say start here to not cause infinite recursion. Okay. Okay, so maybe we should test some of this scanning facility that we made. So let's say test scan let. So S is a scanner that takes this string here, and we're going to assert that s.popT is token kind keyword let at pos 0, 0. Okay, and let's see. Okay, so in scan identifier or keyword, we're actually peeking past the end of file. So we have to say while not self dot at end of file, because we can't peek at a character once we hit the end of the file. And yeah, let's see. Okay, that's looking better. Token kind, we didn't add identifier to it yet, so let's add identifier to it. Okay, so now we just need to parse let expression. At least that's what our tests are telling us. Okay, so pop keyword or error. Okay, so we already peeked that let was the keyword. So we're going to actually put a comment here that says cursor is past the let keyword on entry. So when we enter this function, the let keyword has already been dropped because we're going to drop it here. Okay, so that's our let keyword. We're dropping it on the floor and we're entering over here. So now we need to parse the name, which is going to be an identifier, and then the equal sign, and then the right-hand side expression, the keyword in, and then an expression. Okay, so first we got to start by grabbing a name. So we're going to say pop token or error, and we need that to be an identifier token. And if it's not an identifier token, we'll say expected identifier on left-hand side of let expression. Nice error message. Okay, so we're getting to this not implemented error in the scanner, and that's actually because this is one of the first times that we've encountered white space. This is a space character. So if we want to be white space insensitive, then what we can do is we can just ignore it and continue popping characters. So we can say if C is a white space character, like a space, then we return self dot pop T and recurse. And of course, we'd probably do it iteratively in real life, in a real application, because we would not want to cause deep recursion in our scanner. But this at least gets us past that point. So parse let expr. Okay, so we parse an identifier. And so ultimately we want to do something that does like return our let, and our let takes the left-hand side, which is our string, so that'll be toke.value, right? That's the payload inside of the token. And it's going to take a right-hand side, an expression, and a body. Okay, so now we parsed our left-hand side. Now we have to pop token or error token kind dot equal sign. Expected equals sign after left-hand side of let expression. Okay, and so that'll cause an error if it's not right. I don't think we have support for equals in our token kind, so we're going to have to go and add that. Equals. Great. And so now in our scanner, we'll add support for equals. And really should factor this into a table at some point, but for expediency, we're not doing too much factoring. All right, so now we've popped our equals without error. And so now we have to parse the right-hand side expression. And the right-hand side can basically be an arbitrary expression. So we just call parse expr, and that gives us our right-hand side. Now, and you see we make it past that point. Now we have to look for this in keyword. So one of the things I like about this syntax is it shows that the let is nicely an expression. So if you put a semicolon after here, then it looks more like some of the languages that we're used to, the modern ones like a Rust or a Swift or something. But the in kind of, at least in my head, makes it look like a expression where we say, this is like something mathematical I'm saying, where let this name be this expression inside of this other expression. And that's what the in is indicative of. So we're going to have a keyword called in, and this kind of follows in the footsteps of SML or OCaml. These kind of ML-based languages have this in-based syntax, which we're kind of mimicking here. So here we're going to pop token or error, pop keyword or error, excuse me. We want to, so we have peak T as keyword, so we want to say pop keyword or error. So this is a slight variant where we know we want it to be token kind dot keyword, but also we want to say that it also should have this payload in the value field. So we want this to be the in keyword. Okay, so let's say, so this is not going to compile for us because we want to have pop T or error have an analogous pop keyword or error self target The target is going to be a string because that's how we encoded keywords. We're going to have a message if it cannot. The result is going to be a popped token. If the result kind is not a keyword, or the result value is not the target, we're going to raise a parser at the position, and we're going to say expected target keyword got result token, and then put our error message there. So it's pretty similar. Probably would factor that. And okay, pop keyword or error. So we're going to say expected in keyword after let binding. So after the right-hand side, we'll say let right-hand side just to make it a little clearer. Okay. So we expected an in keyword, but instead we got an identifier. That's a little slightly surprising. So we said let identifier equals expression, and in our case, expression here. So we've not taught our parser how to turn an identifier into a name ref, like we said that we wanted it to be in this test case. So in parse expression, we need to go to our grammar, and we need to say that we can have these. A term can be a number or an identifier or a parenthetical expression. So down way at the bottom where term is, we're going to say if the peeked at token kind is an identifier, because this is a fairly atomic thing, we're going to say parse name ref. And so just like parse number is a fairly simple parsing routine, we're going to say parse identifier, and that is going to return the name ref expression. So we're going to pop this token. If the token kind is not token kind identifier, we're going to raise a parser. We probably have an opportunity to use our helper routine in both of these, but just pattern matching. Expected identifier got this token, and we're going to return name ref of token.value. And so it's going to need us to define name ref. So a name ref is an expression, because when we refer to an identifier like x, that is indeed an expression. And so the name reference will have a value, which is a string, which is what it's referring to, the name that it's referring to in the current environment. Okay, so we're going to need to define a notion of equality here. So other is object returns bool. We're going to say return is instance other name ref, and self.value is other.value. And we're going to need that for our unit test. Okay, so pop keyword or error. So expected keyword got identifier value in. And that's because we did not teach the scanner that in is actually a keyword. The only keyword we taught about was let. So let's do a little bit of due diligence here. Let's create this. Let's create this static data that says keywords. And that's going to be a frozen set that includes let. It's going to include in. What are the other ones that we had defined yet? I forget, but the unit test should tell us. So we're going to say if the identifier keyword is in the keywords set, then we know that it should be a keyword. Now finally passed the pop keyword or error point. Great. So we popped in. Now we have to parse the body, which is yet another expression. Okay, parse name ref, it is not happy about. We called it parse identifier here, so we make those names consistent. Okay, it's complaining now that the let object, which we now are able to create, does not have an attribute right-hand side. This is correct because it has children. So right-hand side is the 0th child, but that's a little bit confusing to access as indexed members in these children. So let's make a nice aliased property that returns self.children0 for the right-hand side, and then body returns self.children1 for the body. Okay, so now it's happy. So now we're able to bind values in these let expressions and refer to values as well. But if I did something like this, y plus x, it doesn't give me an error at parse time. It gives me an error in my expectation. But ideally, we would be able to detect errors when we're referring to names that have not yet been bound or not been bound in a correct way. So next video, we'll look at how to create bindings that record the current environment of what has been bound and checks that you can only refer to names that have been bound in the current expression environment.